Hello, everybody. Hello. Welcome back. Welcome back, everybody. Let's start the last session. So in this last session, we have two excellent talks. The first one is from Xiao Wang. He'll be talking about BitGC, garbling with 1 bit per gate. And he has promised me there's at least one funny slide.
Yeah, multiple. Thanks, Mike. We already saw this slide, and by the way, this is the old slide, so we actually have 2 routes. So Dave already talked about the first part. So now I want to talk about the second part. That is how to garbling with stronger assumptions. And the first question is that, okay, so why we want to do that? That's because there has been awesome results in this year crypto showing that with random oracle, with mini-crypt 1.5 times security parameter is pretty much the best you could do. So we really need to actually look for stronger assumptions to actually do better. Okay, so today I'm going to first talk about the garbling scheme that actually just communicate 1 bit per Boolean gate. And then I'm going to talk about the progress that we have made in implementing this scheme. And of course, so BitGC is one of the recent progress in making garbling small. There has already also been quite a lot of related and relevant works. Some appears in crypto. That's partially why we have 3 sessions on garbling, and also some on Fox this year. So I want to say that the train of BitGC has not departed yet. So if anyone still wants to hop on the train, now it's the time. After today's 2 talk, you should have all the background to hop on this train. And of course, there's no physical BitGC train. It's from AI. Okay? Yep. So let's first think about why the classical Garbled circuit is so big. Okay? So we already have all the fundamentals of the Garbled circuit, so I'm not going to repeat them again. So how the Garbled circuit works classically, we send encryptions of C on the different combinations of input garbled labels. That's how we do it. Okay? And then the evaluator is going to try to decrypt one of the row and obtain one of the labels. Okay? So the problem here is that because the encryption has to contain the information about the key, then this encryption cannot be smaller than the size of the key because the key has to be transferred in this case. Okay? And so we don't want to really have that. Okay, so we want to think about the GC in a kind of different way that is actually relevant to Dave's talk. Okay, so we're not going to think about the labels as labels, but instead we are going to deploy free XOR. Hope everybody's memory is still fresh. We are going to deploy free XOR and think about the labels as secret shares of value times free XOR delta. Okay, so now the 2 parties hold secret shares of value times delta. The goal of the garbler is to send some kind of encryptions of the output shares under the input shares. Okay, so we are sending some kind of shares under some kind of shares. Okay, and then at the end of the word, they should still hold shares. Okay, so in this case, let's think about what kind of information needs to be transferred. Okay, so the delta is the fixed delta across the whole circuit. So ideally, we can kind of amortize the transferring of the delta over the whole circuit. Then this part really just needs some information about some bit, because we no longer need to transfer the keys. So it's really just to need to contain information about the bit. Okay. So in this perspective, so the blueprint of the whole protocol is so Garbled is going to first send some kind of encrypted truth table bit. So truth table is just some bit. So we are going to send the encrypted version of the truth table bit. Okay. And then, hopefully, we want the 2 parties to find a way to derive the encryption of the output in some way. Okay? And then once they have the encryption, we want them to perform a local operation such that they can convert the encryption to shares, which actually has been known for years, for multiple years. And I'm going to mention them later in the talk. Okay? But the challenge here is that, because the evaluator doesn't send information to the garbler, garbler is not going to be able to hold this ciphertext. So garbler cannot directly, compute this ciphertext because this ciphertext depends on the secret and the garbler, and this is just one way, one message. So there's no way for garbler to obtain this ciphertext. Okay, but if we actually look at this whole process as a whole, that can still be doable. Okay, so we are going to have a protocol that distributively evaluates the truth table truth table bit, and in the end, they are going to get the secret shares of the value times delta. Okay, so everything is still in shares. Okay, so that's the blueprint. Okay, but this is like too vague, so I'm going to start with some technical details. Okay, so first I'm going to going to present a Garbled table that actually has a point and permute in it. Okay, so here, so this is nothing but just like the classical Garbled circuit for a AND gate that is shuffled by 2 bits, pi A and pi B. Pi A and pi B are the color bit for those who actually who still remember some part of the Garbled circuit that David mentioned an hour ago. Okay, and this is really just a AND logic permuted by these 2 bits. Okay, so if the evaluator obtains one of the A and one of the B, the evaluator will be able to find one of the row, strap out the hash, and obtain the label. Okay, this is just like the classical point and permute Garbled circuit, written explicitly with a H, where H is let's say a random oracle. Okay. Okay, so now, once we have this, the Garbler is supposed to randomly pick both of the output label, and the evaluator will be able to evaluate by actually pointing out one of the row and decrypt it. Okay, so everything is a classic. Okay, so now our first step in obtaining the final protocol is that we are going to apply the Garbled row reduction. That is, since all the output labels are picked uniformly, now we are not going to pick them uniformly. We are going to pick C Z00, one of the labels, such that the first row equals to 0. Okay, that's one of the celebrated results. So in that, once we set that, the first row of the Garbled table is 0. Okay, and the remaining rows can still be written explicitly by swapping out one of the C to other values. Okay. So far, still, everything stays in a classical Garbled circuit that everybody knows. Okay? You can trust me about the math so far. Okay? There's nothing you cannot, so everything for now is still symmetric key. Okay? So now I'm going to take a leap. Okay? So I'm going to assume that the random oracle is actually homomorphic. Homomorphic in the sense that it satisfies this property. Okay? This property seems to be pretty random. It is pretty random. It is actually not the way that we come up with the protocol. This is just the way that I come up with to present the protocol. So this is pretty random. But we are going to assume that the random oracle satisfies this relationship. Okay, it's like, so what it is doing, so if I is 0, then the first term are the same. Okay? If I is 1, then the first 2 terms are different. And if the first 2 terms are different, then there will be an extra term here. Okay? If the second term are different, then there will be another extra term. Okay? And if both of them are different, then there will be another term, yet another term. That's a kind of what it is trying to, what does it mean by homomorphism here, okay? So once we have this, we can cancel out many, many terms in this table, okay? So in the first row, the second part are the same, and the first part are differed by 1, because this is pi bar, and this is pi, okay? So we got hash of delta comma 0, followed by the rest part of it, okay? And similarly, you can apply the same homomorphism on all of the rows. And once we apply them to all of the rows, we get this simple formulation. Okay? So now, if we think about it, it is actually some kind of encryption of 3 bits on the delta. Okay? So these are the 3 bits that are actually got encrypted. And the delta can be thought of the keys to encrypt these 3 bits. Okay? Of course, assuming that we have this kind of homomorphism on the RO. Okay? Any question? Okay, so once we have this, okay, so if we can have this, the whole process can still be done. Okay? The garbling can still be done by Garbler sending these 3 values instead of the original Garbled table. But this is still big. This is as big as the classical Garbled table. Okay? And the evaluator can still evaluate this table because, well, this table is no different from the previous table. They are just this is just a different way of writing it. Okay? This is just a different way of writing it. So everything is still good. Okay? But the problem is that this is not small. Okay? This is not small yet. Okay? So what we hope is that if there is a way to send the ciphertext of bit efficiently. And if there's a compatible way of instantiating this homomorphic RO, then our job would be mostly done. Okay? So we want to find a way to send this cheaper than actually sending this kappa bit ciphertext. Okay? So how can we do that? Well, I mean, if we just stay in the symmetric keyword, that would not be very easy. But like, let's say if we actually assume a somewhat homomorphic encryption, then it becomes much cheaper. Okay? So let's say if we want to send an encryption of a bit x, what we could do is that we can send a encrypted seed. Sending a seed is small. I mean, assuming that PRG has a bigger extension rate. And then like two parties can locally like expand the seed to get encryptions of bits. Okay? And then in order to obtain the encryptions of a bit, they can just send the difference between the uniform bit derived from the seed and x, the bit that we want to send. And once we send the delta, with the difference, which is just a bit. Okay? The parties can homomorphically XOR D back to the ciphertext to get the encryptions of a bit. Okay? So we can use this method to instantiate these three rows. Okay? Remember that our goal is to send encryptions of this bit, and this bit. Okay? So now in order to send the encryptions of these three bits, we are going to use like a somewhat homomorphic encryption to send the bit in this manner. Okay? But because we use like, and we just need a PRG that is good enough. And there are many this kind of good like PRGs, and one big class is dark matter. Okay? And this is actually the dark matter from NASA's website. So this is actually dark matter. Yeah. Okay? So now, okay, so we more or less solved the first problem. That is how to transmit this truth table bit in the garbled table. Okay? And we're kind of mostly done with that part. Okay? But the problem here is that like the ordinary garbled table has bit strings as labels. Okay, but like now we are actually like talking about mostly like lattice-based encryption schemes. So they are no longer compatible with bit strings as labels. Okay, so we need to define our labels not as bit strings but as like a polynomial ring element now. So every label is now a polynomial ring element such so that the scheme is compatible with somewhat homomorphic encryption scheme. Okay, so and also like we are like instead of defining like the language for one based on 0 and XOR delta, we're going to define it in a slightly more complicated way. Okay? But the goal is to obtain the last equation. Okay? The goal of defining them in a different way is to ensure that the last equation still looks nice. Okay? So this is, I mean, like you can actually try like a value 0, and when there are 4 possibilities, you can try it. Actually turns out that it works out. Okay, so the last one is the most important thing. Okay, so now okay, so what we are going to do is that okay, so now instead of like we are going to send like encryptions of 3 bit, and these 3 bit are going to be written in this way. Okay, I'm like so how did I come up with this 3 bit? These are really just the ring adapted version of the original like delta encrypted tables. Okay, so that's the original version. Now, because we are working in polynomial ring, things has to be algebraic. So we convert them into algebraic representation of the original values. Okay, so now, like to send this 3 bit, it becomes easy. We can just use the slides that I mentioned like a few slides ago. Okay, so for the Garbler, like is going to define the output label using a eval function. And the evaluator is going to also evaluate the output label using the eval function. And this eval corresponds to this distributed evaluation that I mentioned earlier. Okay? So the two parties hold some kind of secret sharings of the 2 bit of the 2 input values as v times delta in some way. And we want to have a eval such that this kind of relationship still holds after this gate. Okay? So this eval is essentially corresponds to the way that we want to instantiate this homomorphic random oracle. Okay? This homomorphic random oracle will become this eval for distributed evaluation of this garbled table that contains 3 bits so far. Okay? So compressing this from 3 bit to 1 bit is actually easy because like these are really just some homomorphic operations on pi A, pi B, and pi C. So if you allow like 2 more levels of homomorphism, you can compute this by sending just the encryptions of pi C. So this step is that it becomes much easier. Okay. So we want to instantiate this homomorphic random oracle, which looks like this. So the way that we want to instantiate is that, okay, so we want to have kind of similar syntax, and such that if I is different, then there should be one term. If j is different, there should be another term. And if both of them are different, then there will be yet another term. Okay? Okay, and if we further assume that decrypting a bit using, we want to construct the scheme such that it has this property, okay? This is pretty much, this is like a GSW, or it's directly like a GSW-like a property. Then we can expand this decryption into the corresponding terms in the Garbled table that we constructed, okay? This is like a long-term, but it can actually be further simplified into a equation that looks pretty, far more elegant. Okay, so now we have this. Okay, so I'm going to claim, I claim that this evaluation function will allow us to maintain this kind of constraint that we want in the Garbled table. Okay, so we have properties on these two sides. Like the Garbler is going to compute this function on their labels and the table, and the evaluator is also going to compute the same thing. Okay, and I argue that they will actually be the right relationship. Okay, this is the most math-heavy slides, but I'm going to go over them one step by one step. Okay, so the first step, there's nothing. Okay, so I just replace pi a VA by pi a XOR VA, pi a XOR pi a XOR VA. So it's identical. Okay, how did this goes to this? Well, here I'm invoking the properties of eval. Okay, so this is one side of the eval. This is the other side of the eval. The difference will essentially give us this, because this is the other side of the eval, and the difference is this part. Okay, you can plug this as I and this as j. It will give us this equation. Okay, and then I'm going to invoke how we define the labels. We can actually get this part, subtract with this. It will give us the zeros label, because you can trust me on the maths. Yeah. And we are going to, so essentially what I want to say is that if eval is defined in that specific way, and that we define the labels in this specific way, when they compute this local computation, which is called distributed eval, they will get some ring element, polynomial ring element, that still satisfy the relationship that we want for the Garbled circuit. Okay? Yep. So essentially, so what's happening, the real overall flow of the protocol is that the Garbled first obtains pi c in some way that I don't want to talk about because it's too much detail. And then the Garbled sends the difference between pi c and RC, where RC is a fresh random bit. Okay? And then the two parties can use encryptions of A, encryptions of B, and encryptions of C to assemble these three ciphertext, which are essentially just some kind of low-degree combinations of these three ciphertext. And once they have these three ciphertexts, they can locally compute this distributed eval function that, if you believe me, will actually give us the right output labels. And that's pretty much it for the overall flow of the protocol. Okay, any question? No? Okay. So the last task, so the invariant still holds. Okay, so we still have the labels and the encryptions of the color bit here. Okay, so the last task is to come up with a design for this eval function. That's the last step. Okay, so what do we need for this encryption scheme? We need the encryption scheme to be able to homomorphically evaluate a PRG, so that we can send the encrypted bit efficiently, and two more levels to assemble this truth table, because truth table has pi A and pi B, different combinations of them. That requires two levels of multiplication. Okay. Beyond that, we need the decryptions of the message equals to message times delta, and this giant evaluation property. These are all the properties that we need. If you can satisfy all these properties, then you can plug it into the BitGC paradigm. Okay. Well, for the first one, you can either use GSW, which is probably the most natural choice, because GSW directly gives this property. Or you can just pretty much use any lattice-based encryption scheme and send a encryption of delta on the delta. And then before you decrypt, you just multiply it with delta of delta. That would extend any pretty much we get actually pretty much any somewhat homomorphic encryption scheme to support this one. Okay, so that's the easy one. So difficult one is this one. Okay, so this equation. Okay, I'm going to spend a few minutes to explain how to construct this one. Okay, at least I want to convince you that this is constructible with small cost. Okay, this is like too big. It's it's too long. Okay, and as long as something is long, we want to decompose it into small parts. Okay, so we can imagine this eval function to have multiple parts, and the different parts, the difference of different parts, give us different terms. Okay, so we can kind of construct eval incrementally. Okay. So the first part we want to do is, okay, so what to include in eval such that their difference gives us this term. Okay, well, it turns out that actually, so that property is really just like a key homomorphism for the lattice-based schemes. Okay, so this can be written as this one. Why? Because if I is 0, then it's just A pi A. If I is 1, then it's the other one. So it actually is this. Okay, so here we are saying that the difference of the decryption should be the difference of the key decrypting the ciphertext. So this is a key homomorphism. Okay, so how to obtain key homomorphism? That part is actually straightforward. This is easy. I mean, especially we are working on lattice-based schemes. They have every property that you want, pretty much. Okay. So similarly, we can also use the same property to construct the second part. Okay? It's pretty much it's the same. Okay. So the difficult part is the last part. Okay. So we want to have to add something to the eval function such that the difference gives us I times j times the decryption of the third ciphertext, and that's kind of the difficult part. Okay. So for the first part, essentially, we just need a near linear decryption algorithm that actually gives us all the properties that we need. Okay, so it's a paper 6 years ago, so quite some time. Okay, so let's say, so I think here I'm writing let's say if we have some simple lattice-based encryption scheme. Essentially the paper is saying that if you have a sufficient gap in the plaintext space and the noise budget so that you don't overflow and you don't do modular operations, then the properties will hold. Okay, I think the majority of the authors are actually here, so I don't want to talk too much about it. Yep. Okay, so that would complete this part. The remaining is really just something else. Okay, so how to construct this something else? Okay. Because of our naiveness, we actually call it deck tilter, which is actually a bad name, but bear with me with these names, so that when you read the paper, you will be able to align with our notation. Okay? So what we really want is that, okay, so we want some operation such that if both parts are different, then they will actually decrypt and get some difference. And if one of them is the same, then they should hold the same value, where the difference would be 0 because I and j are 0. Both of them are 0. So the output is different only if both of the first two arguments are different. Okay, so how are we going to do this? Well, so from the high level, so first step is that we want them to be able to locally, from this input, to compute some kind of labels z such that one part gets z, the other part gets z plus item j. So essentially, their value are the same if one of the ions and if one of them is 0, and they will be different by delta if both of them are 1. Okay, so this gadget can also be viewed as secret sharing of I times j and times delta. Okay, this is also called the succinct homomorphic max by a set of authors. And the semi-private HSS by another set of authors, and we call it a deck tilter. But this is pretty much, this is a very important tool. And if you saw one of this name, or deck tilter, that's the thing that we are, part of us are referring to. Okay? So once we are done with this, the next step is easy. We just want to convert delta correlation into some other correlation. So that can be done by just invoking the somewhat linear scheme again by using this tool stuff to decrypt the ciphertext that we are targeted to. Okay, because like if both of them are 0, then they are holding the same z, then they get the same output. If it's different by a delta, then they will actually use this scheme. They will have a difference of this. Okay, so the last slide that I have, and then the whole scheme, this whole process would give us the stack tilde. And this stack tilde would give us eval, and the eval would give us the way to distributively eval the garbled circuit that contains just 1 bit. Okay, well, the last slide is going to be like constructing this box, but it's fine if you cannot understand my next slides, because I'm sure like Rachel is going to probably talk about something on this line as well, so you have another chance to understand it. Okay, so the garbler and the evaluators like start with this kind of labels, and they want to hold that value. Okay, so the first step is that we are going to expand these values into the actual values that it represents. So in practice, this is actually the parties need to, I and J is pretty much like the color bit, but I don't want to write them as color bit because you may forget about color bit. Okay, so once we write them like that, our first step is that we are going to convert one of the correlation from delta to a different delta. Okay, this is really just so that we can use the standard ring-RLWE assumptions. Okay, and once they convert into different delta, it just so happens that, okay, so if you work hard enough, you will find that some local multiplications of them multiplied with a different gadget that just multiplies different versions of, this is some uniform A times delta A hat, and this. The inner product of them will actually give us the right correlation. Okay, how we come up with this? We spend a lot of time thinking about, it's we made it up. It's I cannot really come up with the intuition, but this is the gadget that you need. And once you send this gadget, this can be used across the whole circuit for reducing the value to this kind of correlation. Okay, and the math actually works. Turns out that the math works, and the garbler is going to have this value, and the evaluator is going to have that value plus I times j times delta. Okay, so that's. This is the slides that construct this kind of a key tool that we need. Okay, and finally about some concrete efficiency. So we have made some small progress in making it more concrete. So the first thing is that we optimize some part of the PRG, and also optimize some part of the gate assembly. And in particular, we kind of reduce the number of levels of somewhat homomorphic encryption by actually just use additive homomorphism to assemble the gate. So that increases the communication a little bit, but we feel like this is something we need to do in order to have a speed that can get the paper accepted. Okay. Well, it also has important practical meaning, but I don't want to talk too much. Okay. In the end, the speed is about 10 microseconds per gate, okay, which is a terrible speed in the Garbling community, okay? But if you actually plug that into F1, then you get a much faster speed, which is maybe usable, okay? So our conservative estimation is this speed based on what they have. It turns out that they have the parameters that we need directly, so this is kind of a pretty good estimation. Okay, so I guess so what is 100 gate or 10 microseconds per gate means? So that's about the speed of TFHE that support like a bootstrapping for every gate. Okay, that's about the same speed of TFHE. But the TFHE and Garbling, they are two completely different primitives for different purposes. So it's not really apple to orange comparison.
What is the comparison with standard Garbling?
So this, for any circuit, it would be like this gate. We didn't pose any restriction for the circuit for this. So for any circuit, if you tell me the AND gate and XOR gate, I can. So that number of gate multiply 10 that microsecond, that would be the total time.
Maybe you're missing something. I'm asking comparison with old school Garbling.
Oh, so for EMP toolkit, you can garble 220 million gate per second.
Okay. That's okay.
Yeah, and I will report this number again. So in the end, I want to say, okay, so what 10 years can actually do to everyone, okay? So 10 years ago, slightly 10 years ago, like Usenix 2004, we have the first implementation of garbled circuit. I actually dig there and try to find the garbling speed. That's about 0.1 second per gate. Okay? Roughly 10 years later, it is optimized to 100 nanoseconds per gate. I mean, it's like 10 to the 5, 10 to the 6 orders of magnitude improvement. Okay? So things. Yeah, hardware is also part of the progress, right? Yeah.
How much time to run Tetris on this machine and this machine?
Yeah, I mean, here, like when I say 10 years, I'm not saying 10 years of crypto community. I'm saying 10 years of humankind, right? We are optimizing everything. We are optimizing everything, right? So some things changes a lot, but there are also other stuff that didn't change. So I was actually in the audience when you were giving like talks 10 years ago. And I mean, there wasn't much change like on Evolve, okay? And I was talking to Dave, and Dave made an interesting observation that it seems that Siemens doesn't use the eraser that frequently. It appears to be the same one. Yep. So for BitGC 2025, it's 0.01 second per gate. Okay. 10 years later, when we have BitGC crazy, who knows what's going to be the speed? Okay. So yeah. So that's my last slide, and I'm happy to take questions.
We have time for a quick question if we do it while wait till it's setting up.
Just like you said that 1.5 lambda per gate is kind of optimal. I don't think that we know any lower bound.
There is actually a paper in Crypto 25 showing that that's.
Let me finish the
sorry.
sentence. I don't think that we have any theorem that shows us that you cannot achieve something that is smaller than the circuit size, even information theoretically. So disprove this hypothesis.
So, like, yeah, thanks. And but like in many cases of garbling, the application of garbling, the circuit is usually public.
Sure.
And in that case, like, there's no need to translate the circuit, right? There is reusable garble circuit and succinct garble circuit that goes sublinear.
Open question. Prove that it's impossible to go from information theoretically. As far as I know, this is open.
I see. But there exists protocol that goes sublinear.
It's some sort of model. So what are the restrictions on the model, I guess, is the question.
The lower bound holds in some very concrete model.
Yeah, I guess it depends on the model, yeah.
Well, right? I mean, but the basic question is open. So.
Yeah, you maybe find the model that can show that this is a lower bound.
That's a funny thing to say. But
Oh, you have one. Oh, interesting.
question.
Okay, I think we'll have to thank Xiao again.